Esteemed colleagues and fellow researchers, I am Teng Zihao from UESTC. Today, I am excited to present our latest advancements in the design of low-complexity frequency-invariant beamformers. Our work focuses on addressing the challenges posed by the beam squint effect in wideband sensing and communication systems. My presentation is divided into 4 parts, which are background, system model, problem formulation and solver, simulation results, and conclusions. Let's begin by discussing the background of our study. Wideband sensing and communication systems offer several advantages, primarily due to their high data transmission rates. However, directly applying narrowband arrays to wideband systems can lead to beam squint effect. This effect can significantly degrade the system performance by altering the main beam direction as a function of frequency. Frequency-invariant beamformer design can be utilized for mitigating beam squint. There are some existing FI beamformer design techniques, such as the least square approach, convex optimization-based method, STFT-based method, and AAT-WLS. Among them, this square approach has a low side-lobe level, but it cannot achieve precise side-lobe level. Convex optimization-based method can realize precise side-lobe control, but it has a high computational complexity. STFT-based method has high implementation efficiency, but it is only applicable to uniform arrays. AAT-WLS is applicable for arbitrary antenna arrays, but it has high computational complexity due to the matrix inversion involved in each iteration. Most recently, array response control-based methods have been presented with precise control of the beam pattern in arbitrary arrays with low computational complexity, but it is only limited to narrowband scenarios. Motivated by the superiority of ARC, we present a new FI beam pattern synthesis framework with high flexibility and low computational complexity. With an understanding of the challenges posed by beam squint, let's now delve into the system model we used to address these challenges. Let's consider a wideband signal whose frequency is band limited from Fmin to Fmax, and the temporal sampling frequency is Fs. The signal is observed by a linear wideband array with m elements, each connected to an n-type FIR filter. The time starting point is negative n-1/2. Then the array response can be expressed as follows. The propagation time delay between the mth element and the reference point is tau m theta equal to dm sin theta over c, where dm is the position of the mth element, c is the speed of light, and the gm f theta denotes the pattern of the mth element, which can be obtained by actual measurement or full-wave simulation. I will now explain how we reformulate the problem and solve it. The FI beamformer is designed to have a frequency-invariant window shape, and the side-lobe level in Fi theta s is lower than a given bound rho Fi theta s, which means for all Fi theta s in F theta s, P Fi theta 0 equals to 1, and the absolute value of P Fi theta s less than rho Fi theta s. The aforementioned problem can be directly solved by convex optimization, but it has a high computational complexity. We adopt a novel approach utilizing an array response control-based method, which significantly reduces computational complexity. This method is inspired by adaptive array theory and involves spatial response variation constraint to maintain the desired beam pattern. First, we introduce SRV-Constrained as shown on this page. Since the SRV matrix is the non-diagonal Hermitian semi-definite matrix, it can be regarded as the covariance matrix of a virtual colored noise to realize FI beam pattern synthesis. A keystone of ARC-based methods is to use a virtual interference plus noise covariance matrix in the minimum variance distortionless response beamformer to suppress the noise and interference. Hence, we deduce the modified MVTR problem P1 as follows. The problem P1 can be easily solved as shown on top of this page. Let's consider a single frequency interference at FI-I. We can express RIPN as follows, and define Q tidal equal I plus epsilon Q and applying the Woodbury lemma. Further omitting the common factor for brevity, the optimal weight vector is written as follows. It is well known that the beam pattern at the point of interference depends on the INR. The higher the interference power, the deeper the null in the beam pattern. Thus, the accurate beam pattern control can be realized by turning the optimal complex factor, which is a function of INR. We modify lambda OPT iteratively equivalent to dynamically adjusting INR to ensure that all the points of beam pattern satisfy the given constraints. The accurate ARC can be realized as shown in this page. For any phi k from minus pi to pi, the normalized array magnitude response at fk theta k can be accurately controlled to a given rho k, which leads to a phase ambiguity issue. The selection of phi k may severely influence the beam pattern performance. In wideband sensing system, an appropriate phi k can be selected by maximizing the beam pattern magnitude response at f0 theta 0 to improve the target detection performance. Thus, it led to the problem P2. The problem P2 is equivalent to the following problem and it has a closed form solution. As a case step, a frequency entry point fk theta k in the xylem region, where the error response varies most from the constraint is selected, and the proposed FI beam pattern synthesis scheme is summarized in algorithm 1. The primary computational burden of our algorithm lies in calculating lambda k, leading to a low complexity of O(m)n squared per iteration. We give a complexity analysis of the proposed algorithm. We report the computational complexity of other recent design approaches in each iteration. Their comparisons are listed in table of the bottom of this page, which illustrates that the proposed algorithms are flexible in every structure and has a lower computational complexity. Let's look at the simulation results. The first example is an FI beam pattern with a notching requirement to suppress strong spatial interference. A uniform array with 40 isotrophic elements is applied to synthesize the desired pattern, where each element is connected with a 24-type FIR filter. The desired beam pattern is shown in the left bottom of this page. For the proposed for compression, the STFT CPR and the original SRV optimization algorithm are included. The beam patterns are shown in Fig 1, and Table 1 lists the comparison results. In Table 1, shows that the FI beam pattern synthesis by STFT CPR cannot reach the desired saddle level, especially in the low frequencies. The FI beam pattern synthesized by the proposed method and the original SRV optimization have comparative FEEs, but the proposed method is more efficient with less CPU runtime. Next, we illustrate the performance of the non-normal direction focused FI beam pattern of mitigating beam squint. Consider a 16-element uniform array, where each element is connected with a 22-type FIR filter. The beam is focused at 20 degrees. The top views of the beam patterns are presented in Fig 2, while Table 2 provides a comparative analysis of the results. As observed in Fig 2, all FI beam pattern synthesis techniques effectively mitigate the beam squint phenomenon. However, the FI beam pattern synthesizer using the STFT-CPR method falls short of achieving the desired side lobe level. Conversely, our proposed method not only attains the minimum FEE but also requires less CPU runtime. The last example is an FI beam pattern with a uniform side lobe synthesis for a 16 isotrophic element non-uniformly spaced linear array, where each element is connected with a 32-type FIR filter. The beam patterns are shown in Fig 3, while the synthesis results are shown in Table 4. From Table 4, we can see that the AATWS approach fails to achieve the desired side lobe level. The proposed method yields the lowest FEE of 0.2 with a shorted CPU runtime of 0.84. We successfully applied our design across the different array configurations, showcasing significant improvements in side lobe control without increasing computational demands. The results were particularly promising in scenarios involving non-uniform arrays where traditional methods fell short. In conclusion, we proposed a new SRV-Constrained ARC framework and developed a new low-complexity algorithm for FI beam pattern synthesis to mitigate beam squint. We derived the FI-MMR principle to mitigate the phase ambiguity issue. Numerical results are carried out to validate the flexibility and efficiency of the proposed algorithm, make it practical solution for real-world applications. Thank you for your attention. I look forward to your questions and a fruitful discussion.